In this class, we will continue our discussion of how we evaluate differences between groups by evaluating differences in mean scores. Specifically, we will discuss the t-test. From our last class, we learned that while technically the z can be used to test differences between sample means, we will have trouble using the z because we rarely know the variance in standard error of the dependent variable in the population. So we need a test statistic that will allow us to use a substitute to estimate the variance and standard error in the population. And these estimates will come from the variance, standard error, and standard deviation and standard error in the sample. So the t-statistic, or the t-test, can be used to test hypotheses concerning one or two means when the variance in the population is unknown. So just like the z, the t, and then ultimately the f test and chi-square test have unique sampling distributions. And the best place to start is to learn about each of these distributions. The t-distribution is the sampling distribution of sample means when the sample variance is used to estimate population variance. In contrast, the z-distribution is the sampling distribution of sample means when the population variance is known. It is similar, the t-distribution is similar to the z-distribution in a number of ways. First, like the z, the t is a symmetrical distribution that ranges from plus infinity to negative infinity. But unlike the z, the t-distribution approaches the normal distribution as n increases, a phrase you'll recall from the central limit theorem. Thus, unlike the standardized normal distribution, the t-distribution changes shape depending on the sample size, or n. Your text by Spats does a good job of demonstrating the way in which the t-distribution changes as n changes. See page 158 of the 8th edition of Spats to coincide with this discussion. If you look at that drawing on page 158, you will notice that at lower sample size, or degrees of freedom, the kurtosis is lower, the shape is flatter, and there are more values in the tails. But when there are higher degrees of freedom, the distribution is taller, thinner, and with fewer values in the tails. This highlights a general trend I've mentioned before with distributions, which is that all things being equal, as n increases, as sample size increases, the distribution becomes taller and the frequency of the distribution decreases. To cite a practical example, imagine you have a blanket lying on a floor. As you pick up the blanket from the middle and slowly raise your hand, the middle of the blanket, or the curve, becomes taller and the blanket becomes thinner. And there are fewer and fewer values in the tails. The tails of the blanket begin to creep in from the outer reaches. Before going to the next slide, see if you can answer this question. As the t-distribution becomes thinner, taller, and with fewer values in the tails as n and degrees of freedom increase, what is happening to the critical value that we use to test hypotheses? The answer is that the critical value becomes smaller and smaller. Perhaps the easiest way to see this is to look now at the t-table in your text. First, you need to locate the column of the table that presents the results for a two-tailed test when alpha is equal to 0.05. From the table, you should be able to see that the critical value we would use if we had 10 degrees of freedom is plus or minus 2.228. And the critical value we would use if we had 20 degrees of freedom is plus or minus 2.086. Look through the column And notice how the critical value decreases as n, or degrees of freedom, increase. Now notice one last thing. When we have an infinitely large sample, or degrees of freedom is infinite, the critical value for the t-distribution equals the critical value for the normal distribution, plus or minus 1.96. This demonstrates an important relationship between the two distributions, that at infinite degrees of freedom, the t-distribution is identical to the normal distribution. So what are degrees of freedom? For the t-test, degrees of freedom are computed merely by taking the sample size minus 1 or 2, depending on the situation. In the next class on the t-test, we will learn to use when to use n-1 or n-2. But technically, degrees of freedom refers to the fact that we lose a degree of freedom every time we compute a mean score. That means that if we were to have a sample of 5 numbers, say with a mean of 20, we could vary the value of 4 of those numbers. I mean, we could change them in value in any way we would like, but the 5th value would need to be fixed in order to still wind up with a mean of 20. Thus, the degrees of freedom for the sample of 5 is n-1 or 4. Or we essentially lose a degree of freedom when we compute a mean. I would urge you not to spend too much time trying to understand this technical, theoretical explanation of degrees of freedom, and you certainly won't be tested on it. But rather to spend your time focusing on remembering when to use different types of degrees of freedom and how they are used to find a critical value. You can always come back to this brief explanation or to the one in your text if you'd like to have a little bit better description of what degrees of freedom means.